Thank you. So I'd like to start by thanking Trygve and Stura for organizing this conference and giving us a chance to all come together to discuss one of our favorite subjects. I use the word almost in my title. I like that word. I like Henry Schaeffer's statement, the right answer for the right reason. I like to describe density functional theory as almost the right answer for almost the right reason, at almost the right price for almost all systems of interest. And I think that's what it is. But here it's a slightly different meaning. Almost present at the creation means that I wasn't there when Lowenberg and Cohn and Sham did their work. I came in somewhat later, maybe 7 or 8 years later. But the field really hadn't gotten off the ground yet. There was interest, but I think the interest in solid state physics developed after about 1972, 73, when I started to get interested in the subject. So I'm going to focus first on the early history of density functional theory in condensed matter physics, because that's my background, that's where I came from. And then I'll touch briefly on its early history in chemistry. Although I missed some of that, I also can say something about it. So before the 1970s, I believe that most electronic structure calculations in condensed matter physics were done with the Hartree approximation, in which, in Cohn-Sham language, that means you set EXC and VXC to 0. You ignore the exchange correlation effects. I know there was also the X-alpha method since the early 1950s, and some people in condensed matter physics were using that before the early 70s, but it was not so widely used, I believe, and I'm not sure why. Anyway, the Hartree approximation is very old. It goes back to 1927. Hartree made a slightly more elaborate version, which eliminated the self-interaction error from the Hartree approximation. And the version that condensed matter physics people were using was based on a simplification of that, in which you drop the self-interaction, explicit self-interaction correction terms. Hartree actually used that method to do atomic calculations in the late 1920s. And so you might ask how he did that, because there were no computers. Until maybe after World War II, computers were not accessible to academic scientists, except maybe if they were working in weapons projects. So, the story is that Hartree had a father who was a retired engineering professor, and he liked to work with mechanical calculators. And he actually did the first self-consistent calculations with mechanical calculators. Very clunky devices where you do the arithmetic one step at a time on the human time scale. That's kind of remarkable. Anyway, the Hartree approximation has some serious limitations, as you know. It strongly underbinds atoms, and it strongly atoms in molecules. It yields bonds that are too weak and too long, and it yields vibrational frequencies that are too low. Nevertheless, it was used because I guess it was what we knew how to do at this time, in that time, and it seemed to have some blessing. So I guess we could say that modern density functional theory began with the paper by Cohn and Sham in 1965. If you read that paper, it's interesting that the main text of the paper doesn't say there's an underlying exact theory. And it's only in a note added in proof that they say, oh, we realize that this is just this LDA is an approximate realization of an underlying exact theory. I asked Lou Sham about that a few years ago, and he said that they actually did realize that it was an exact theory, but they forgot to put it in the paper. So anyway, in 1965, I started my graduate study at Cornell University, and I didn't hear about density functional theory before I graduated in 1961. In my dissertation, I used the Hartree method, and I started a postdoc with Cy Bosco at the University of Toronto in 1971. But we were also using the Hartree method. We were using the Hartree method to calculate electron-phonon interaction. So I still use the Hartree method there. And what I finally learned about this Cohen-Sham density functional theory was in 1973. And that's when Mark Rassault, who had been a graduate student with me at Cornell, moved from a postdoc position at the National Research Council in Ottawa, in Canada, to the University of Toronto to work with Cy. And when he came into the group, we had group meetings, we had group talks, and basically Mark told us that this theory is working. This LDA is working much better than the Hartree approximation in solid-state calculations. And that was a motivating factor. Our whole group switched from Hartree method to LDA, and that was the beginning of my interest in density functional theory. So I always assumed that the Cohen-Sham paper was very little cited until 1973, because I guess that's when I heard about it. But history isn't always what we remember it to be. And so to prepare for this talk, I went to the Web of Science, and I looked up the citations to the Cohen-Sham paper, and you could order them in time. So you can see how many times this paper was cited before 1973. It was actually cited about 310 times from 1965 to 1973, which is a pretty good citation rate. Since then, it's been cited 53,000 times, which is a vast under citation, because if all the papers that cited that used the Cohen-Sham work actually cited the Cohen-Sham paper, it would have between 500,000 and 1 million citations. But that usually doesn't happen. So yeah. So I looked at some of these early citations to the Cohen-Sham paper from 1965 to 1973. I didn't read even the abstracts of all of them, but from the titles, I read some of the abstracts, and it gave me a sense of what people were doing. A lot of the citations were mentions, rather than applying the theory or developing it. They simply mentioned it, that this theory exists. But not all of them, of course, and so I'm going to list a few that I found that were either pioneering applications of the LDA or attempts to go beyond the LDA to better approximations. So this is not all of them. It's just a few, but it's a few that I'd like to mention. There was a paper in 1966 by Tong and Sham. They calculated the energies and densities of atoms with good results. There was a paper by Bennett and Duke in 1967. They did metallic interfaces with this method. Not just bare surfaces, but the interface between two different materials, planar interface between two different materials. There was the paper by Ma and Bruckner in 1968. That was one I knew about very well. where they developed the gradient corrections. Actually, it was the gradient correction for the correlation energy. And they even proposed a generalized gradient approximation because they realized that the gradient expansion by itself was bad, much worse than LDA. And so they found a way of summing it up in an approximate sense. There was work on phonon dispersion in LDA by Shaw and Pin. In 1970, there was a very important paper, which has been mentioned before in this meeting, the paper by Norton Lang and Walter Cohn, where they calculated the metal surface energy. Actually, they did the gellium surface energy first, and then since that is negative for high-density gellium, they introduced the lattice effects perturbatively with the pseudopotential, and they got good results for the surface energies of metals. Surprisingly good because the LDA was supposed to be for uniform gas, and maybe for other periodic solids which somehow resemble the uniform gas, but it was not expected to work for such a strongly inhomogeneous system, and yet it did. There was work by von Barth and Hedin in 1972, where they developed a local spin density approximation and parameterized it with the random phase approximation. I think the LSD appears earlier in the Cohn-Sham paper, but I think without a parameterization. Anyway, those were some of the important papers. Let's see if I skipped anything. Oh yeah, here are some more. There's a paper by Janik, Williams, and Baruzzi in 1972. They did the band structure of copper with a local density approximation. There was a paper by Geldart, Rassault, and Taylor. They were all at the NRC together in Ottawa, and they evaluated the second-order gradient corrections to the correlation energy, including the density dependence of the gradient coefficients. They did that within the random phase approximation, and they found that the gradient correction, just as von Bruckner had found before using the high density limit of those coefficients, that the second order gradient approximation was much worse than the LDA, and in particular the correlation energy was terrible because it was positive with the gradient corrections for nearly everything. So anyway, Mark Rassault was coming out of that work, and he came to Toronto and told us about that work. And that's how I started to get interested in density functional theory. And I think I was very lucky to be in the right place at the right time. But it was only on my second postdoc, when I went to Rutgers to work with David Langworth, that I realized that this theory was something I wanted to work with for a long time. Maybe I didn't realize it would be my whole life, but a long time, because I got deeply interested in it. And that's because David Langworth wanted to understand why the local density approximation worked and why the second order gradient expansion did not work. Because I think it was sort of natural to assume that if you get something that's right for the uniform gas, then you make it right for an electron gas of slowly varying density, slowly varying but non-uniform density, you expect things to get better. They don't get better, they get worse. And David was very interested in that. And he was, in a sense, well equipped to investigate that problem. He had a strong background in many-body physics from his graduate work with Leo Kadynov at the University of Illinois. And he extended the adiabatic connection fluctuation dissipation theorem from the uniform electron gas to a system of inhomogeneous density. That had actually been done earlier by Harris and Jones. And the difference is that in Langworth's work, the density is held fixed for all interaction strengths between non-interacting and fully interacting. With Langworth, we also found that the exchange correlation hole, which underlies the exchange correlation energy, satisfies several exact constraints in the local density approximation, but those constraints are violated, and violated very badly by the second order gradient expansion. And that was reported in this 1975 paper. So I learned a very, very valuable trick from David Landreth, and that is that if you want to make an approximation right, you take out everything that's wrong in it. And that essentially is what we did with the second order grading corrections to make the first GGAs. There was a GGA by so in Landreth, in my work with Landreth before I left Rutgers, we established why the LDA works, why the second order gradient expansion doesn't work. We explained that in terms of the hole properties, but we didn't actually have a modern GGA. And the modern GGA was developed first by Landreth and Mayle in 1983. I had a version with Wang in 1985. Axel Becke had a version in 1988 for the exchange. And there was the LIP functional for correlation from Bob Parr's group. And in 1996, with Kieran and Matthias Ernzerhoff, we developed the PBE GGA, which is still very widely used in materials physics. In 1976, there was a beautiful paper on density functional theory by Gunnarsson and Lundquist. This paper has been referred to several times before. I guess I can tell you now that I was the referee of that paper, one of the referees. It's a very nice paper. I think their work was essentially independent of the work that Landreth and I did. They also identified the exact constraints on the exchange correlation hole that the LDA satisfies and that the second order gradient expansion does not. And they gave a very nice summary of density functional theory, including why it works and what it can do. So anyway, in 1977, I had been a postdoc for 6 years, and I was wondering if I'd ever get a faculty job, but I did at Tulane University. So I started there. And in the physics department, and when I moved there, I was very surprised to find that there was a faculty member in the chemistry department who was also a maven for density functional theory, and that was Mel Levy. Mel was coming out of Bob Parr's group, same group that produced Wai-Tao Yang and Paul Ayres and many other important theorists in density functional theory. The most notable thing about Bob Parr, I think it's been mentioned before, Wai-Tao mentioned it, is that Bob Parr loved new ideas, especially good new ideas, but I think he loved all new ideas, to tell you the truth. So he was very open, and he was probably the first senior chemist to be interested in density functional theory and to try to understand it and improve it. So after a few years at Tulane, I started to learn about Slater's method, the X-alpha method, and I got interested in that. I had not really heard about that before. This is, again, I think there's a certain narrowness in every field, and physicists probably the majority of physicists probably had some bias against that method too. So I got interested in that as well, and I read Slater's book on the self-consistent field in atoms and molecules. Still a beautiful book. I recommend it to you. It has a lot of insights, and in particular, I learned in that book that when you use the X-alpha method and calculate the dissociation limit of a molecule, you don't end up with integer charges on the atoms. You end up with fractional charges, which is wrong, of course. Separated atoms don't have fractional charges unless you're separating something like H2+, where it's possible where the electrons in a sense have to be shared. So that interested me very much, and I started thinking about how can this problem be solved, and how does the exact density functional theory solve this problem? And after thinking about that for a while and discussing it with Mel Levy and Bob Parr and Jose Balduz, who was actually an undergraduate researcher at Tulane, we came up with the idea that the energy is the exact energy as a function of fractional particle number is linear between two neighboring integers, and that at each integer electron number there's a discontinuity of the derivative. The energy itself is continuous, but its derivative jumps discontinuously. And that led to this Perdew, Parr, Levy, Balduz paper from 1982. There was also a paper with Mel Levy about the band gaps in 1982 or 1983, and it attributed the failure of the band gaps in LDA to a derivative discontinuity. So in the 1980s, Mel Levy formulated, actually in the late 70s, in 1979, he formulated his constrained search version of density functional theory, which is a much clearer and shorter proof than the original proofs, and is also more constructive in the sense that it actually tells you in principle how to construct the exchange correlation energy by constrained search over wave functions. Of course, that's not practical. You don't really want to search over many wave functions to find the right one, but it tells you exactly what this functional is. And in the 1980s, Mel derived many of the known exact constraints on the exchange correlation energy, and in some cases I collaborated with him and derived some of them too. But I think at that time, most theoretical chemists were not really interested in density functional theory. And they were probably more interested in Hartree-Fock and other wave function-based methods. And then a phase transition seemed to occur at the International Congress of Quantum Chemistry meeting in Mentone in 1991. And I was not there because I didn't go to chemistry meetings in those days. In those days, density functional theory belonged to physics. I went to physics meetings. Sometimes I went to joint meetings where chemists as well as physicists would speak, but I didn't really go to a pure chemistry meeting until somewhat after 1991. Yeah, my first pure chemistry conference was in 1994. That was in Prague, I think. But anyway, Gabor Čanka was there at Mentone 1991, and I asked him what he remembered from that, and his recollection was that as a member of the audience, what he saw was that John Popel gave an invited talk on the first day of the meeting. You can correct anything that's here, feel free, because recollections are it's hard to make recollections completely accurate. But anyway, on the first day, John Popel gave an invited talk, which was not about the DFT. But after the talk, he was asked about DFT, and he said that he would only be interested in it if someone showed him a correct binding energy curve for a molecule. And the second day, there was an invited talk by Walter Cohn, and he showed such a curve. Now, Gabor didn't remember what molecules were shown or what the source was, but just as a speculation, it might have been the H2 and H2 plus curves from Gunnarsson, Janssen, and Lundquist from 1975. It might have been some of Bob Jones's work on molecules. I'm not sure. But anyway, the binding energy curves were kind of reasonable. They didn't have the right binding energy. The molecule was overbound, but the minimum was at the right internuclear distance, and the curvature around the minimum was approximately right, so you get the right vibrational frequencies. And when Walter Kohn said that, he said that he would reconsider density functional theory, and of course he did. Now, at the same meeting, I'm sure that Axel Becker was there. I believe Mel Levy was there as well. And I believe they also talked with John Popel at that meeting. And so there may have been many influences that converged to make him interested in density functional theory, at least for a while. And of course, in the 1992 and 1993, Axel Becker proposed the hybrid functionals that started with a GGA and then or an LDA or a GGA, and then mixed in a fraction of exact exchange. And I think that was probably also influential in bringing more chemists into density functional theory, not only because the hybrids were in many cases more accurate than the GGAs, but also because I think the chemists liked exact exchange. They were comfortable with it, and they didn't want to throw it away. So this was a way to save some of the wave function character in the functional. And I remember many conferences. I went to many conferences in chemistry in the 1990s because DFT was a hot topic then. I remember one in which Nick Handy announced that he was going to find the exact density functional from neural networks. Well, at that time, I didn't even know what a neural network was, and I'm still not sure I know what it is. But but anyway, I heard Nick make that announcement in many talks at many meetings, and then I went to a meeting and he didn't say anything about it. And of course, I didn't want to be impolite and ask the question in public, so I privately asked him later, how's that work going? And he said, well, it didn't work. but of course, he was ahead of his time. So now, nowadays, it works much better. And many people are working on it. So in 1998, Walter Kohn and John Popel shared the Nobel Prize in Chemistry for density functional theory and for computational methods. And Walter, whose last chemistry course was in high school in Austria, told me that after he received the Nobel Prize, he returned to the University of California, Santa Barbara campus, and suddenly the chemistry students knew who he was. So as he walked across the campus, the chemistry students would come up to him, speak to him, and some of them asked him to help them with their chemistry homework, which he couldn't do. Now in 1996, I had two excellent postdocs in my group, Kieran Burke, who's here today, and Matthias Ernzerhoff. And together we constructed the Perdew-Burke-Ernzerhoff generalized gradient approximation. And what was new about that is that previous GGAs had been constructed to satisfy exact constraints on the exchange correlation hole. But all these exact constraints on the exchange correlation energy had been derived throughout the 1980s and later. And we wanted to use those, so we designed PBE to satisfy as many of those known exact constraints as a GGA could satisfy. It can't satisfy them all. And that led to the PBE GGA, which has about 200,000 citations. So it was a physical review letter. It turned out it's the most cited physical review letter of all time. It's not fair that this paper gets 200,000 citations and the Kohn-Sham paper gets only 53,000. That's the way it goes sometimes. And then in 2001, with postdoc Carl Schmidt, I proposed what's called the Jacob's ladder of density functional approximations. That's based on the story in the Old Testament about Jacob, who's crossing the desert, and he lies down, he puts his head on a stone and falls asleep, and he has a dream about, he sees the angels ascending and descending a ladder between heaven and earth. And so the Jacob's ladder, so what this term means. It was just formalizing what Axel Becker and I and other people had been doing for a long time, which is to try to expand the number of ingredients, and before that Langworth as well and other people, try to expand the ingredients in the functional. And each time you add another ingredient to the exchange correlation energy density, the energy is always an integral over three-dimensional space of some function of some ingredients. Each time you expand the number of ingredients, you can either satisfy more exact constraints or you can fit more data or both. So at the lowest rung of the ladder, which I've actually listed on top here for simplicity, we have the local spin density approximation. And the only ingredient it uses to find the energy density, exchange correlation energy density of position R are the local densities there, local spin densities. The next level, and that's the zeroth, that's the first rung. The second rung is the zeroth rung is the Hartree approximation, which I'm not listing here. The first rung is LSDA. The second rung is the generalized gradient approximation, where we use, in addition to the local spin densities, the gradients of the local spin densities. But of course, we can't just do the second order gradient expansion. We have to generalize that expansion so that it cuts off in the right way when the gradients are too big. Third rung of the ladder is the meta-GGA, which uses the orbital kinetic energy density. The fourth rung is the hybrid functional that uses the occupied orbitals. You could mix in some exact exchange. I now put the self-interaction correction on this fourth rung as well, because it also uses the occupied orbitals, but in a different way. And on the fifth rung, we have the RPA-like approximations, which make use of the unoccupied orbitals. So as we climb up toward heaven, we're getting closer to traditional quantum chemistry methods, which use the virtual orbitals. But we use them perhaps in a simpler way in density functional theory. So I left Tulane University for about 10 years and went to Temple University. And while we were there, Adrian Roginski and Janwei Sun and I developed, Janwei was my postdoc at that time. We developed another functional called SCAN, strongly constrained and appropriately normed. And that functional was designed to satisfy all 17 of the exact constraints that a meta-GGA can satisfy. So this is a meta-GGA. It's a limited form. It can't satisfy all the known constraints, but it can satisfy 17 out of about 20 or 22 known exact constraints. And that actually had quite good results, both in chemistry and even more in condensed matter physics. Now I'm interested in going back to the self-interaction correction that I started working on with Alex Zunger in 1981. I'd like to see if I can develop a self-interaction correction that is accurate. The Perdew-Zunger self-interaction correction takes any functional and makes it exact for all one electron densities. It turns out that that's purchased at a high price because the self-interaction correction sort of spoils the functional for anything that's not a one electron density. And if you have a slowly varying density or a uniform density, the self-interaction correction makes serious errors. Well, how serious is an error? It makes a few % error for the uniform gas, but that's enough to screw things up. So I'm interested in trying to apply this self-interaction correction. I've actually been able to make it work for the LDA. So we have a scaled self-interaction correction which is scaled down in regions of slowly varying density. It works very well for LDA. It makes the LDA about as good as PBE, maybe a little better in some cases, particularly for barrier heights and other problems that have a strong self-interaction error. It's very good. And I'm also interested in strong correlation and symmetry breaking and in a possible connection between those things. so I'm going to go back to Stur's comment after Whitehouse talk about how you can interpret symmetry breaking as a kind of dynamic density fluctuation, describing a dynamic density fluctuation with a small frequency. I like that point of view very much. I think for actual molecules, that's exactly what we're seeing when we let the symmetry break. We're not seeing a real symmetry that persists over a long time, but we're seeing a density fluctuation that persists over a relatively long time on the microscopic scale. In condensed matter physics, symmetry breaking is real. It's real. There are many solids that cannot be understood in density functional theory without symmetry breaking, and in fact, experiments cannot be understood without symmetry breaking. And an example of this would be the antiferromagnetic solids, where spin symmetry is clearly broken, and you can actually measure the magnetic moments that result from that. The experiments show that. And that's because I believe the fluctuation is occurring over such a long time scale that no one can ever observe it. And that's because solids are big and they have high barriers, I believe, to conversion between one state and another, and therefore very low frequencies for this fluctuation. So for me, it's been a fascinating journey, a long journey. And for me, and I think for most of us in this room, density functional theory is evergreen. So thank you very much.
Thank you very much for an inspiring talk. So, any comments or questions? Yes, up there.
Very nice presentation. Thank you very much. I pick up on the word strong correlation, and in the solid state community, there are other ways than what you have described to handle that, dynamic and mean field theory, for instance. Would you be able to, is it meaningful to try and put DMFT onto your Jacob's ladder, and which rung would it then be, or is it another ladder one would have to consider to place it somewhere? Can you comment on this?
Yes. So DMFT perhaps gives you a more microscopic view of what's going on at a higher cost. I don't think it's exactly a density functional theory, although it uses density functional theory sometimes as an ingredient, particularly for the environment of an atom or an ion in a material. I'm not sure if I would put it on the ladder. My way of understanding strong correlation, which may be wrong, and I think we'll hear from Gus about this. We'll hear more from Gus about this. But in many cases, strong correlation can be mimicked by symmetry breaking in density functional theory. The classic case of this is the stretched H2 molecule that we heard about before, where the singlet spin symmetry breaks and you get a full electron spin up on one side and a full electron spin down on the other side when the separation is large enough. That's a symmetry breaking, but it's a symmetry breaking that almost perfectly describes the strong correlation in stretched H2. There are some other examples too. There are a lot of examples in condensed matter physics where symmetry breaking in DFT mimics strong correlation. There are a few other cases in chemistry that I know about. One of them is the singlet carbon molecule, or actually the singlet ground state of the C2 molecule at equilibrium. So even at equilibrium, there's a strong correlation and a symmetry breaking. And I think maybe beryllium-2 that we heard about is another example where in Hartree-Fock the spin symmetry breaks, and then you get a much more reasonable description of the system. I don't know how general that is, and maybe we'll have some discussion of that in Gustavo's talk.
Thank you.
Yeah, so now that you mentioned symmetry breaking in C2, now when you do chromium-2, you get further off from the right result.
That's right.
So
With scan, yeah,
yeah.
we know that. But that doesn't mean that you won't get the right result with a better functional. So C2 is unlike H2. So at H2, any functional you use will break the symmetry and give you a good description, a reasonable description of stretched H2. In C2, it's rather different. C2 at equilibrium, LDA symmetry breaking doesn't give you a very good description of the atomization energy or the singlet triplet splitting. PBE, GGA, still not very good. When you get to scan, it's perfect. The singlet triplet splitting and the atomization energy are, you don't see any difference between scan for that molecule, accuracy of scan for that molecule, and the accuracy of scan for other molecules. So what's possible, in my view, and I'm not sure it's true, is that as you improve the functional, you're able through symmetry breaking to describe more and more systems that are strongly correlated. So there have to be improvements beyond scan and R2 scan. For instance, a self-interaction correction to those functionals, or maybe a hybrid correction might be better.
So PBE is obviously a very successful functional, and one may consider this as a non-empirical one. But the empirical element is the choice of the constraints to satisfy. Now, my question is, what was the motivation to choose those constraints and not others, which are also possible? Or the other question, what happens if you choose other constraints with the performance? So has anybody tested this in detail? For molecules and solids, maybe?
Yes, I think so. I think in particular in PBE, you have to make a choice between getting the right gradient second order gradient expansion and satisfying another exact constraint. And you can't satisfy them both at the same time with the GGA. You can do that with a meta GGA. You can satisfy both of those constraints at the same time. But yes, the simpler the functional, the more you have to select your constraints carefully. If you have a good enough functional, I think you could, in principle, satisfy all the known exact constraints and hopefully get a good result.
I have a couple of comments. One is up on the screen we can see that scan satisfies all 17 known exact constraints. What John actually meant to say was all 17 remembered exact constraints.
Okay. I should have known you would bring this up, Kieran. That's true.
So it turned out that there were 2 exact constraints known at the time that John forgot about. But it turns out that it does satisfy those 2 extra constraints, which shows a certain consistency. If you get a lot of these constraints right, you get some of the others right. But it didn't have to. And those 2 constraints were proven by a couple of obscure DFT guys called Levy and Perdew. So there was no excuse for that one, John.
I'm going to appeal to my age here as well. Get a little forgetful.
And just one point since we're talking about historical things, when we did the PBE paper, the original functional was PW91, and my job as John's postdoc was we were going to write the full derivation of PW91, and John had the idea of doing what became PBE, and I, in my infinite wisdom, gave John a really hard time over, just reworking PW91, and I said we have no chance of, getting it accepted by phys rev letters. So I'm just giving you this as an example of the wisdom of youth. Fortunately, John persisted. Oh no, and he was the boss.
Yeah, sometimes exact constraints are satisfied even when you don't impose them. And for instance, the local spin density approximation was designed to satisfy what I call an appropriate norm. It was designed to be exact for the uniform gas. No other exact constraint was imposed, but it turned out that it satisfies 8 other exact constraints just because it's the exchange correlation energy of a real possible system. Not maybe a real possible, of an unreal possible system, right? Uniform electron gas is not real, but it's possible. You can write down a Hamiltonian, and you can solve the problem to high accuracy with quantum Monte Carlo. And doing that was enough to satisfy 8 of the 17 exact constraints that SCAN satisfies.
More? Are you still searching for useful constraints?
I welcome them. The most recent one, I guess, goes back to work I did with Kieran and Adrian and some others, where we have not actually proved it yet, but there's a Lieb-Oxford lower bound on the exchange correlation energy, which is rigorous, but it's not very tight. It's not a tight bound. It's rigorous but not tight, and that was imposed on the PBE in its construction. But more recently, we speculated that the exact exchange energy satisfies a very tight lower bound. Not exchange correlation, just the exchange satisfies a tight lower bound. So we actually imposed that tight lower bound in SCAN. We don't have any proof of that tight lower bound yet, but one thing that happened as a result of that is that Elliot Lieb and his colleagues and collaborators like Matthew Lewin and others were able to prove a tighter lower bound on the exchange energy that not quite as tight as the one we believe in, but much tighter than before.
So, what's your view on exact exchange? You seem to indicate it was good to introduce it because it made chemists comfortable. Oh.
Well, it makes functionals accurate. I'll tell you why I've always sort of shied away from it. It's because we don't really have, at least initially with the global hybrids, we didn't have any way of establishing how much exact exchange you need except by experience, right? More recently, I think there are some range-separated hybrids which impose some exact constraints and work very well for solids.
Can I ask you? You seem to be looking ahead at more parameter fitting, and it sounds a little depressing to many of us who love to think about things physically, and you're the prime exponent maybe of this view. Could one think of entering this parameter space in a way where the parameters had physical meaning, and that you actually learned about the physics of the system you're looking at when you use those parameters and find what their values are supposed to be? Just to give you one example, suppose that you decided that you wanted a functional which would do the right thing for all the involved atoms. And then you took that to the molecules. And then you could see that, okay, there are certain problems that are, if I turn them off, those parameters, then of course I've got my atoms, but they're not well treated, so they bring some problems to the molecule. But if I now have a functional with parameters that do the right thing for the atoms, then I know that the error that I'm now looking at is of molecular origin in some way. So that, in other words, could you make this parameter fitting a physical type of analysis instead of just a random statistical analysis?
Right. So in a sense, that's what we did in SCAN and R2 SCAN.
Yeah.
R2 SCAN is a sort of a more computationally efficient version of SCAN. We used appropriate norms. So one of the appropriate norms is the uniform electron gas. But when you get to the meta-GGA level, you can make functionals very accurate for the total energies of atoms and also for the ionization energies of many atoms. And so we use the exchange correlation energy, the known exact exchange correlation energies of the rare gas atoms, which are not bonded. So we wanted to avoid anything that comes into a bonding calculation. And we fitted the functional to that, among other things. And that works. It gives very accurate energies for atoms. And then you start to see problems developing in molecules and solids because of incorrect charge transfers. So because the functional is still semi-local, it still has this convex behavior that Whitehow talked about. And the biggest error of SCAN in molecules and solids are these charge transfer errors. If you have a system that can't have a charge transfer error, for instance, if it's all made up of all identical atoms, then everything is great. But if you have different atoms and you can have a charge transfer error, then larger errors can appear. And I think your question is very good. And I think the right way in the long run will be to impose the exact constraints on the fitting. So fit to data, but fit a functional that is constrained. I don't think anybody knows exactly how to do that now. One way to do it is through penalties. You could just sort of penalize the functional if it appears to be going away from the exact constraints. There may be other ways too. And I think that could lead to very high accuracy. But I think the exact constraints are needed to make the functionals predictive.
Is there any fundamental reasons for the higher level, for functionals which are at higher level of the Jacob's ladder, they perform not always better, sometimes worse, for ferromagnetic solids, for magnetic moments?
Right.
Not for the description of ground state. Ground state is, of course, we all know, greatly improved. But magnetic properties are not always better, sometimes worse.
Yeah,
the
that's
fundamental reason, or just.
Well, we're trying to understand that now, so I know what you mean. The problems typically appear for the magnetic metals, iron, cobalt, and nickel.
Correct. Yes.
And PBE gives, even LSDA gives a reasonable magnetic moment. PBE is better. And then when you do SCAN, it gets worse. And the errors are maybe 20% in the magnetic moment. And we're trying to understand where that comes from. And it could be for several reasons. One reason is that even the relatively limited amount of non-locality that enters a meta-GGA, there is some non-locality, some non-local dependence of the functional and the density because the orbital kinetic energy depends non-locally on the density, and that's an ingredient of meta-GGAs like SCAN. So one possibility is that it's because even that very limited non-locality is too much for a metal. In a metal, the exchange correlation hole is very localized around its electron because of perfect screening at long range, which is a characteristic of a metal. So one possibility is that. There are other possibilities that we're also looking at.
Okay, I think we close there. Thank you very much for